And I say yes, and then I'm not muted anymore. Okay, so welcome to class October 30th, where I am a pirate. And today is the first class we're going to talk about guards. Just as a reminder to things I've already said, we've got about, including this one, we've got 10 classes. These on November 10th and 20th will be delivered remotely over Zoom. I'm planning to do that at the class time and record it as always. Okay, so let's go to today's material. Hey,
Nice hat.
thanks. So locks must die. So this unit is based on some research that was recently published at eScience 2025. And so we've spent a fair amount of time looking at locks in this course. And one of the things that we've learned about locks is that they block, right? That they have this busy waiting semantics to them. And most science codes still depend on locks, right? I mean, because nobody has anything better, right? So they're in all kinds of codes, databases, workflow managers, and so on. And we've seen the problems that we get whenever we block, even if it's not a lock, right? If it's just a get method on the future, we can clog our thread pools and ruin our parallelism. Locks are also difficult because, as we discussed earlier in this course, they're non-composable, right? And they can lead, and their use leads to all kinds of potential problems. So, the normal approach is to just stoically fix the bugs and moves on. I may have mentioned this before, but like in the MySQL database, there's the paper we found that cited this. They had such trouble with deadlocks that whenever they launch a task, they have a certain amount of time for that task to complete. And if it doesn't complete, they assume that it just deadlocked somewhere and they kill it. So this is a very tricky thing to get right. And these are the bugs that show up in your code, right? So underlocking can create correctness bugs, right? You get race conditions and whatever. Overlocking can kill your performance. It can just make everything sequential but more complicated. Blocking semantics are conducive to deadlocks, right? And we've discussed all these pitfalls before, and it's hard to avoid them all, as you've already discovered in your programming exercises in the course so far. Here's this same example that I showed you earlier in the course. So imagine we have a class that has integer fields A and B and lock A and B. And we have an incr A method and an incr B method and a toString method. If the incr A method correctly locks, increments, and unlocks, likewise the B method, but if they also just happen to println, then println is going to lock A and B. Now, these are reentrant locks. And so what this amounts to is this function is locking first A and then B, and this function is locking first B and then A. You can't see it by reading any individual function. You have to read multiple functions to realize that this is happening. And the fundamental problem that's going on here is when I'm writing this toString method, I don't know what locks I'm already holding, right? That's a problem, is any method you write, when you enter it, you could already be holding some number of locks that you just don't know about. And that's what causes the danger for deadlock and the non-composability. There have been several attempts to kill locks. Transactional memory is something we're going to go into in a bit more detail later on in this course. What transactional memory does is it takes a sequence of operations and it just sort of optimistically changes them, right? But it makes the changes only visible to one thread. And then when the transaction block comes to an end, it tries to lock all the memory that was involved in the transaction. It verifies that all that memory still had the same initial value. And if it does, then it commits all those things. And if it's changed, then it throws an exception and rolls back and starts the transaction again. So transactional memory is a solution that was proposed to make parallel programming easier. And it generated a lot of excitement for a while. And there were even some hardware implementations put out by Sun Microsystems and IBM to try and facilitate it. But the hardware tools didn't get used. Transactional systems support for them has been slowly fading away. It turns out that transactional memory is a bit harder to work with than people expected. And so it looks like, transactional memory could still make a comeback, but on the way, currently it looks like it's on its way out. There are lock-free data structures. We've discussed several different things in this course. Like just recently, we had our deck with that's lock-free, and by using tricky compare and set and other logic, we can make it work. But this is hard to do. It's possible to do, but every time you do it, it's a heroic effort, right? Every little piece of it is difficult. There are some resources to help you in a few cases with some pre-built, data structures and classes, but as a general solution, it doesn't scale well with human minds. Okay, so now it comes to task graphs, and that's the idea that we construct a directed acyclic graph of tasks, like we've discussed in the previous chapter. I don't know that we used the term DAG. I can't remember whether we did. We did? Okay. So, and there are systems that use these to try and in various ways, but they wind up very often using locks in their implementation. And even though potentially they should be a way to avoid them. The actor model is a thing that you should be familiar with from our last lecture, right? And the thing that I'm going to propose here is kind of an actor model. So the objectives in this work, we're going to replace locks as a synchronization primitive. We're going to mimic as closely as possible the semantics of locks that includes condition variables, but we want to be lock-free, non-blocking. We want deadlock to be impossible. We want thread pools to not be clogged, and we want resources not to be wasted on busy waiting. And we want to sacrifice as little performance as possible while maintaining our safety guarantees. And that brings us to guards, which is the topic of today's lecture. So this is a new synchronization primitive derived from task graphs in the actor model. It's fully composable, immune to deadlock, and it has good performance. It's like an actor. It owns a lightweight implicit task queue, the same as an actor does. And tasks with multiple dependencies can temporarily merge the queues of all requisite guards to sort of create the effect of locking multiple locks. And there's continuation-based asynchronous programming style for everything that you do here, which is which you can view as both a plus and a minus, because it's hard to do, as you've seen. Right? When we converted Fibonacci to the asynchronous form, it was great. We got, something that worked well in our task queues, and it didn't block, and we could, scale it up as big as we wanted, but you had to start to think a little differently in order to program it. Okay. So the core operations we have are run guarded, new condition, and run condition. And run guarded is going to be, it's going to be like lock and unlock, but instead of calling lock and unlock around a critical section, we're going to capture the critical section in a lambda and tell the system, hey, execute this when you can, and we'll return a future, or you can return a future to determine when that's happened, but it may or may not happen right away. So it's going to turn stopping and waiting, which is what we do with locks normally, into something asynchronous. So let's see how this looks. So we had this non-composable example, right? With anchor A and anchor B, and we had locks around it. This time we're going to have guard var, which is this guard has sort of a wrapper around a value, and we're going to have GA and GB. And anchor A is going to call run guarded, and it's going to give it a lambda that increments A and then calls the toString method, right? And the way this toString method is going to work, though, is it's going to be asynchronous. So we have a dot then println, okay? And in the toString method, we have a future that contains a string, and we're going to do a run guarded on A and B, and then the future is going to be completed with a string value. So what's going to happen is when I call incr A, it's going to run a task that will increment A and then submit another task to the queue that will do the printing. But the task will run later. It won't overlap with the increment. And so there won't be this adding of locks or guards to the environment that causes deadlock and non-composability. Make sense? Not everybody shook their head. Not everybody nodded. Some people just sort of, yes, Tristan.
This like task scheduling, this toString.
Yeah.
That method has to be void, or can it be anything?
So run guarded is a void. And if we want to return something, typically what you do is you create a future in Java. This is sort of pseudocode. In Java, it would be a composable future, and that you would complete it with a string value. Okay. And so you run guarded, you get the guards for A and B. And when you get the guards for A and B, it gives you access to the values inside the guards. And then you can print them or modify them or whatever. But when this Lambda function runs, you don't know. It's going to run when it can. And that's the thing that makes it work, right? Is instead of running it now, it runs when it can. And that prevents all the problems that we had before. So when it can run, it's always going to try to start with no context. That is, it's not holding any other guards already. The only guards it's going to have access to are the ones you told it should have, right? So in this case, run guarded, right? Oh, this incr A, this method in here only has access to A. It doesn't have access to the A and B needed to complete the toString operation. But the toString operation doesn't run until after this operation. So it all can flow. Make sense? Baron.
Just a recap. They have the guards. Guards are like these very special things. They have like the variable that you want to access. So it's kind of like locked. Yes, they're kind of, but they're not locked, obviously.
They're similar to locks, but they're asynchronous instead of synchronous.
You use this. Okay. So it's mostly like future based.
Yes.
Whenever you want to run the function, you like run guarded. You pass it this special
Lambda, yeah.
It waits until they're available before it does anything. So you're a lot clearer about like the interface that you're using.
Yeah.
Okay.
All right. Tristan.
How is this different than our task pool that we had before? So different that it's not waiting for.
Well, this is going to provide mutual exclusion without blocking our task pool. So the idea is when you increment, when you have a state like that integer variable A and B, right? You only want one thread at a time to be mutating that state. And so the way that you would protect it traditionally is you'd put a lock and unlock in front of it. What I'm saying is instead of putting a lock and unlock in front of it, you create your critical section as a task and pass it to this system to schedule it. Okay.
So it's just like dynamic, like it's like that task system wondering. So
yeah,
you all set up, it just does it for you.
It does it for you, but the key thing is it may not run now, right? And with locks, you're always saying, I want to do it now. And I'm going to stand here and block the doorway until you do what I want, right? Whereas this is more like do it later. Do it when you can. All right. So how does it work? All right. So in this picture, the capital G stands for a guard, and it's got a pointer to an atomic reference that it uses. And we've got three tasks here that we want to run, A, B, and C. And each of them have an atomic reference to a next task. But initially, all of these atomic references are null, right? And that's what the dotted boxes mean. Okay, so what we're going to do is we're going to schedule task A. in the guard. And what we do is we do a get and set, right? The get and set gives us back a null, and A goes directly into the guard's next field. Now, when you get back a null, that means that there's nothing in the queue. Nothing has been scheduled on this guard yet, so you can just run immediately. And so the first task that gets run guarded call just runs. Doesn't wait, it just runs. Which is something that can happen. It could run later, it could run now. In this case, it will run immediately. And then when it's done, what it does is it puts a special value into its own next field. It tries to do a compare and set of this special value, which we've called X for done, into its next field. And we have a green check mark because it's going to succeed. It's going to do it's going to do compare and set from null to done. If that succeeds, everything is finished. Okay, and the guard now has task A in it, and task A's next field points to X. One task of the 3 has been run. Okay, now task B runs. So again, we do a get and set. Task B puts its task into the guard and gets A back. It attempts to push its task. Since B didn't get a null back, right? Now it's going to try to push its own task into the next field on A. It's going to do a compare and set from null to B. That's going to fail. So I put a little X here to just signify that it's going to fail because the next task is not null, right? And because that failed, I know that the task that the guard was running is complete, and I can just run B. Okay, so are you with me so far? Kind of makes sense?
I think we're gonna have to like redo it.
We can
Get some of it.
we can redo it. Okay.
Just checking to see if it needs to wait in line. So it does like a test and set the next pointer if it's still.
A get and set. Well, it's got a get and set and a compare and set. Yeah.
Yeah.
It's doing the compare and set to see if it's done, and it is. So it runs. However, let's assume that didn't happen. Okay, so task C is now going to try to run, and B is still running. B is happily chugging along, doing whatever it does. And we do the swap while B is running. And now what we're going to do, since we're C and we've just put C into the queue, into the guard, C is going to try to do a compare and set from null to itself on B's next field. This time it's going to succeed because B isn't done and B didn't put done in that field. It's still null. So it's going to succeed. And so the thread that put the C in there, when it sees that it succeeded, it's done, right? It said, I've queued my task. I'm not going to run the guard now because it's busy, but I'm done. Okay. Now B finishes. When B finishes, it's going to try to mark the field done. It's going to do a compare and set from null to done, and it's going to fail. And it's going to fail because there's a task in there that needs to run. And so it's going to run it. And this way, only one task can run at a time. One task that's submitted to the guard can run at a time. There's a queue there that is created in memory by these next pointers. Make sense? Yeah, so the last part was, right? We, just like before, when we're done, we try to do a compare and set from null to done on our next field. We fail because another method was queued there. And so that means we run the method. Yes.
Back at slide 21
Yes.
and go through like the whole thing again?
Yes, I will. Baron.
I add a flavor to that as well. So you have like an analogy for this process. You said that there was like a queue formed in memory, that these things are scheduled with respect to a queue. There's a single like guard.
All right, let me try and give you an example, like an analogy. All right. You've got an office worker you've got somebody working at the front desk of the DMV approving licenses. Okay. Can only approve one license at a time. And you can either come up there, you can come up there, and if the desk is free, you can put your thing in there and get it stamped. If it's not, you have to put it in this slot in a box next to the person who's doing the stamping. And they're going to keep stamping. They'll draw tasks out of their box if they have to, and they'll mail it to you afterwards. If they're not free to do it right away. So that's my on the fly analogy.
Okay.
All right. Okay, so let me point. Yes.
How many like distinct kinds of like things are there? There's like the guard, there's the things that are queuing up the guard. Are those the only two types of things here?
There's going to be another type of thing. We're going to get to that.
Okay.
But the idea is, and here's the thing. In the process of enqueuing this guard, I did exactly 2 atomic operations. I did one get and set and one compare and set. And that compare and set was not in a loop the way compare and sets normally are, right? So there's exactly 2 operations to get it into the queue. Which means, and queuing it is wait free if you want to think about it that way. Unless, of course, you're running in Java, because in Java, the get and set operation is implemented as a lock-free thing. But let's not get into that. Okay, so Reagan wants us. Yeah, we'll go back to the beginning. Here's the beginning, right? We have a guard. We have 3 tasks that we want to run. The first task, we do a compare and set with the guard's next field and put A in there. Still, everything's next field except the guard now has a null. Okay. Now A got a null back from the guard. That means it's the first task to run. That means that it can just run. When A finishes, it tries to mark itself as its next field with a done. It succeeds in this case because nothing else has submitted to the guard. So there we go. It gets in there. Now everything is quiet. B now tries to submit a task. It does the get and set with the next field on the guard. It gets back the A. Then it attempts to put itself into the A's next field. It fails because the next field is already marked done.
Why does it try to do that?
It always does that. Whenever it gets something back that isn't null, it tries to put itself into the next field of the task it got.
But so why is it trying to put itself into the next field for A?
What happens is when it got back the that means A is the last task given to the guard. If that task is done, then I can run. If that task isn't done, then A needs to run me when it whatever thread is running A is going to have the responsibility of running my task.
B in A's thing is just making sure that A is already done.
Right. It's making sure that, yeah. So the compare and set operation, the way it works is if it succeeds, then the run guarded method is finished, right? It's queued the task. It's not going to run it, but it's queued it. If it fails, that means that instead of queuing it, it's free to run it. Okay. And so in this case, because it failed, B can just run. And that's why it's colored green. Okay, now while it's running, so just to cover all the cases, while it's running, C does the same thing. It does the get and set, it gets back the B, and now it tries to put itself in the next field because that's what it always does. It tries to put something into the next field, right? Okay, so this time it succeeds because there is nothing there. And so the C is there and run guarded finishes. Now B finishes, the task B finishes running, and it tries to mark itself done by doing a compare and set on the next field from null to done. It fails because there's a task there. And that means that instead of being done, the thread that just ran B now runs C.
So G is like a tail pointer.
Yes. Yes.
So really these 2 memory blocks of C, they're the same memory.
Yes.
It's a bit confusing.
So
I think I got it now.
I think so too. I wanted to see if I could recap what you said.
Okay.
Except for, actually, let me ask one question first. So you said that one of them failed to put it into the next field.
Mhm.
I know that the next field was the previous ones, but the B was already queued up.
Mhm.
Then the C comes in and B is still running. So
Right.
Here goes the next field after B, which is like really it's the next field on B. If you have a second one that comes in, it can't actually put anything in the next field there. So where does it wait? Does it put in the next field for C?
You're gonna have to, you have to run that by me again. So let's look at this picture. You're at this picture, right?
Oh, no, I'm working on the image of the office over here.
Oh, okay.
Yeah, just because that helps me, I guess. I guess if we're this, it's not this picture. I'm imagining if you have like, you have B, that's scheduled up.
Is it running?
B is run.
Okay.
Like A was, it got A was.
Right. Okay. So it's B is running. Okay.
Wait, so each one of these has a next and a done.
No, the next field either contains a task or it contains a special value, which means done. Next can be either of those things.
Okay, so like when the first A comes in, it receives nothing because nobody's been queued up, so it's allowed to just go.
Right.
But then the B comes in, A is like, say, running. A's next field has to be put to B
Yes.
because nobody else has put anything in the next field yet.
Yes.
Okay, and then if somebody else were to come and A was still running, what would happen?
Well, so the key step, right? The thing that's important here is the get and set, right? So when I do a get and set, I take whatever the last thing was that submitted to the queue and I get a reference to it and I put a reference to my task into the guard. So no one else will ever see that value I just got back, right? Because I have taken it. It's no longer in the guard.
Oh, okay.
Right? That's what the get and set does. It exchanges.
Okay, so people would see the next one, so then it just queues up back to back.
Yes.
Okay, okay, that makes sense. And then, all right, I think I'm good.
All right.
Yeah.
All right. Calvin, are you good? Does any of this make sense to you? I could do it one more time. That's a thing I can do. I know this is hard. It's conceptually a little bit tricky. Good. What, Tristan?
I guess you can explain again, but I was gonna ask, like, how can this scale up to multiple threads? Like, if you have, say, if you want to have like a guarded free evaluator structure, like how would you be able to allow more threads? Could you modify it by
So you want to have a read-write version of a guard? Yes, it is possible. But it's not easy, but it is possible. I can show it to you. What's that?
When he was talking about adding more threads to it, I was remembering, I forgot that these things that are coming in are not actually threads, they're just like.
Tasks. Yeah, they're just a block of code, a unit of code to be run.
Okay, so the threads are kind of like what are assigned to actually complete the task in the end, but it's like abstracted for like a thread pool. Okay.
Yeah, there's a thread pool behind this that's running, that's doing everything. Okay, so let's just run through it one more time and see if we're all happy. So the idea is a guard, as well as all the tasks we submit to guards, have this next field on them. And the way we submit a task to a guard is by doing a get and set that exchanges whatever we have with whatever the guard has in its next field, whatever task we want to run with whatever the guard has in its next field. And if we put in a task and we get a null back, that means we're the first thing to submit to the guard. That means we can just run. We don't have to do anything else. It's a special case. It will happen once for each guard. Once a task is finished, it attempts to mark itself done by putting the special value done into its next field. If it succeeds, then everything is done. Everything is quiet, right? Nothing more to worry about. If another task comes in and wants to run, it does the exchange with the next field, just like always. This one doesn't get back a null, so it has to do another step. It has to try and schedule itself to run after the current the task that it got back. And the way it does it is by trying to do a compare and set on the next field from null to itself. That's the way B schedules itself. In this case, it's going to fail because A is already done. And because that means the last task to run on the guard is already finished, it's okay for B to run. Now, while B is running, C tries to schedule itself. So as before, it does a get and set. It gets the B back. And as before, it attempts to schedule itself into the next field of B. Because B is still running, it succeeds. And now the run guarded method is complete. It scheduled itself. It couldn't run right away, but it scheduled itself to run next. When B finishes, it tries to mark itself done. It fails because it's trying to do a compare and set from null to done, but C is there. Since it failed, it knows there's a task there for it to run, so it runs it. Okay.
So this is, I'm assuming just, are there multiple like guards for each thread? Like one thread each gets like a guard list?
Well, you can have as many guards as you want. That's not correlated with the number of threads in any way. It's just the number of things you want to keep mutually exclusive. So
What's the benefit of using this rather than, this is like all running in sequential anyways?
Well, so anything that I want to run with a lock has to run sequentially, right? That's what a lock does, is sequentializes things. This is sequentializing it without blocking the thread. Right? The sequentialization is the guard is there because you need to sequentialize something. The lock is there because you need to sequentialize something. But you don't want to sequentialize too much. And you don't want to block your workers. Right? That's the idea. You're raising your hand?
Kinda, yeah. So I was formulating the question, so there we go. It's the tasks are like little blocks of code,
Yeah.
like kind of like a lock, right? Like you have the lock and the unlock section.
It's kind of like that. I can imagine that there's a lock and unlock section.
But I won't.
Okay. You don't have to.
That's okay. But I mean, like, okay, that's not really the point, I guess. Like whatever's executing the code has to like stop at a certain point. But this is not blocking.
Right.
Okay, so it's still doing like, does it have a loop at any point?
Yes. And when it goes to cleanup, it has a loop, right? And it's gonna try to put that, it's a while loop, right? So what it's going to try to do is it's going to try to put a done in. As soon as it finishes running a task, it tries to put a done in the next field. If it fails, then it runs that task, and then that becomes the next task to run in the loop. And then it tries to mark that one done, and it keeps going until it finally succeeds at marking something done.
Okay. So then that's one task that's completing. The task that's just getting in is queued up. But like when we say queue up, it's like
when it gets queued, it gets put into a next field somewhere.
that's fine.
It either runs or gets put into a next field on some other task.
Okay.
Yes, Tristan.
That's what I'm saying. I thought like the best way to use the system is like you have this kind of like you have a multi-threaded thing. You want to like modify some common data structure. Like I'm assuming that you would have all these threads doing work that would be added to this or modifying it.
Yeah, you would add you would enqueue the work onto the guards.
Yeah, and you have one guard thread that would be like doing those like
whatever thread, any of the threads could run any of the guard tasks. But once one of them starts running it, if they keep piling up, that one will run them all. But if that one finishes, then some other thread can take over running the guard. The guards are not locked to any particular thread. Make sense?
I'm imagining it like it's like the thread pool, except each of the queues is like one of the guards.
okay, I understand. So like, sorry.
No, that was it.
Yeah, except so when you've got the thread pool, the queues on the threads are not the guards. The guards are different queues. They're not.
Oh, you can have both of these existing. at the
Yeah.
same time.
Yeah.
Okay, but it's kind of like that.
It's kind of like that.
Okay.
You could say like, a thread, if they have it, if they're the first one in the guard, but they're gonna be the one that's responsible for running the guards until they run out of tasks on the guard list. So it's not necessarily one specific thread, but it could be like different threads depending on like if they choose.
Sorry, I say that again. I was dealing with a sinus.
So like if the thread is the first task in the guard,
Right.
it's gonna be the one that's designated as the guard thread.
Yep.
That would be running the tasks that are ended in the future. Until it runs out of tasks, and then somebody else takes over when they have tasks.
Yep.
Okay, that makes sense.
Yes.
In the code that you had earlier, you had like the class guard, which was responsible for like running whatever the task was. I say an instance of guard was like GA and G.
Yeah, so I had these things called guard vars. And a guard var, it's a guard plus a piece of data. In this case, it was an integer, right? So this guard was protecting this particular integer.
Okay.
And if you wanted to access it's like a little layer added on top of a guard. So now that you have the guard, you have a concept of a guard var, and a guard var is just a guard and a piece of data that the guard is protecting.
It bundles them
It just bundles them together.
The guard is like, it controls the interface with which you access that data.
Yes.
Okay.
Okay, so guards can never deadlock. And why? Okay, locks deadlock because you might be holding a lock that you don't know about while you get another. And with a guard, that can't happen, right? You're always starting a new context, a new execution context when you run. So you don't have any other guards. Alternatively, you can think of it this way: you're creating your execution as a directed acyclic graph, and you're just appending new dependencies onto that graph, and that's not creating a cycle, and so it's going to work. So that's why it doesn't deadlock. So whenever we call run guarded, we have one or two atomic operations for a guard, and then we're done. No loop. And that's because the first thing is an atomic swap, and then the next thing is a compare and set. Okay, and let's see, what is this example here? So here we have a run guarded that's going to create a task. And, oh no, this is the implementation code. So this is a sample implementation of how you could code guards. It's a bit simpler than what we have in our library that we created. And then we have our guard task, which is a wrapper that contains the next field, right? It's the block of code, right? Our critical section and the next pointer with another guard task. All right, and I just now noticed there's a slight error in this slide because that should say G task, not guard task, but oh well. Okay, so in this one, we say get and set. If we get a null, we run and clean. If the old task.next compare and set from null to new task fails with the bang, then we run and clean. And run and clean looks like this. We run the critical section while our task is equal to this, while our task.next compare and set null to our task fails, we get the next task and we run it. Right? So this is all the code that you need to implement all those slides we just walked through and wrapped our head around. It's pseudocode, but whatever. Tell me when you're done staring at it.
Not done.
All right. So, right, and this is just reiterating the same logic that we walked through, but in text. Now we talk about run guarded for n resources, and this is going to follow something straightforwardly from locks. What we're going to do if we want to get n guards, we're gonna queue up n-1 so-called dummy tasks. We're gonna sort the guards into a canonical order. We're gonna enqueue the first n-1 dummy tasks, which do nothing except stop the guard from running, right? And then the last one is going to run the task, and it's going to clean up all the guards in the set, right? And it's going to do a run and clean up on all the guards in the set. And the first n-1 that it cleans up, it's going to take those cleanup operations. If there's a task pending there, instead of running it directly, it's going to throw it into the thread pool. That way you get potential parallelism. Okay. So if I queue up on 3 guards, when I do the unlock of any of the methods, I could wind up creating parallelism by distributing those cleanup tasks to other threads. Make sense? Okay, that's the way you handle multiple guards. We have some benchmarks that we did to verify correctness. We ran on a we wrote this up in Java. We tested it on various architectures. The ARM there was my grad student's cell phone. It was the easiest way we could get on an ARM architecture. We have an arena benchmark. So we have a bunch of threads perform operations on you have an array of elements, and a bunch of things come in there and just try to modify them at high contention, and stresses the sort of locking and unlocking type operations. And we compared reentrant lock to guard. And higher, I think higher is better on this graph. And it shows that there's a lot of noise in the workload, but generally speaking, we do slightly better than reentrant lock in this benchmark. And then we have a queue benchmark. So we have an equal number of producer and consumer threads that work on a shared queue structure with a relatively small maximum capacity. So you got one queue and you got a bunch of producers and a bunch of consumers, and there's a capacity so that if it gets full, it has to block. Well, not block, but it has to not take new things in, right? And so this stresses things in a different way. And when we tried to run this benchmark with regular locks, we wound up having to use a dynamically sized thread pool executor, because the fixed size one would just lock up. It would all the workers would get clogged up with locks. And this was how it turned out in this one. In this one, we were slightly less performant than the reentrant lock, but it's still comparable, depending on the architecture you looked at. And then we had the accumulator benchmark. So this was what we would do is threads can perform one of 2 operations. You get, like, say, imagine you've got three different guard vars wrapped around an integer, and you're going to increment a random one of them a few times, excuse me, and then you're going to lock them all and increment the smallest one every so often, right? And when we did that, this was our performance. Again, we're very close. There's a lot of noise. But this is the thing that I like. So this is a very small execution. So, but this is what the execution looked like from the IntelliJ profiler tool. So what they're showing you here, is the green tasks are running threads. The red are spin waits, right, where it's sitting there busy waiting. And the black is, operating system doing its scheduling its thing, doing its own internal work. And you notice that with the locks, we've got lots of red all over the place. And with guards, we've got lots of green. We have some red at the end because the system is going to be busy wait on the threads that have no work to do before it can shut down. But anyway, you can see, yes.
Please show us how to do that.
How to do that with IntelliJ? I have to ask my grad student. But there's like some kind of profiler tool. There's some kind of profiler tool there that you run your code, And then I think there's just some option you can pick to make this kind of graph. Yeah, no, it was. When I saw it, I said, you have to copy this from your IntelliJ thing and put it in the paper. And he did. Okay, and then we have implementation. So we have a proof of concept implementation, which we call Java Linear, which is like a soldier that fights with a javelin. We're going to call it Javelin at first, but there was something else named that. And anyway, so we're working on an HPX option, and I guess we don't discuss the condition variables in this talk. I'm going to have to come back to you and do that. Well, maybe I'll just do it with code. Anyway, does all this make sense? Okay, so now let's talk about the condition variables. And to do that, I need to fire up IntelliJ. Do I already have it running by any chance? Yes, I do. All right, so here is our repo that we've got. And the first example I hear is called bank. Have in here is called bank. And here you're simulating a bank with multiple accounts. So we have a static class bank, and it has a balance A, it has a withdraw and a deposit method, right? And it looks, like you'd expect. So withdraw asserts that you have cash. If A is greater than the balance, then it returns false because you can't withdraw more than is there. If the balance is less, if A is less than the balance, then we decrement the balance and return true. Deposit just succeeds. It puts, however much in there. I suppose, yeah, no, it does have an assert A greater than 0. So we're always withdrawing or depositing a positive amount, right? Never negative. We're not depositing negative numbers or anything weird like that. All right. So then what we're going to do is we're going to have a main method where we're going to create a guard var for a bank, right? And then we're going to have a completable future with an integer that's named done. And then I have this thing called loop par for each. So what this is going to do this is sort of a convenient helper. So what this is going to do is it's going to give you, it's kind of like a for loop, right? It starts at I0 and it goes up to IN. And for each element, for each integer in that range, it's going to call a function that takes an integer and returns a completable future of type void. So this is just a way to spawn a bunch of tasks in parallel, right? And then the thing is going to return a future at the end. And if you wait for that future, it means all the parallel tasks are finished. All right, so let's go back to test bank. So in parallel, I'm going to run a bunch of things. And what I'm going to do in parallel is first I'm going to submit a task to the queue to be run, and that task is going to take a.runGuarded. It's going to get the bank, and it's going to try to do a withdrawal of 1 from that bank account. And if it fails, it's going to increment the failure count, right? It's going to sometimes fail because there won't be enough money in there, right? Sometimes when it tries to run, it just won't be able to. And then the other thing is the deposit, instead of running, the deposit is also run in a pool, I guess. It didn't need to, but that's the way we coded it. So, okay, so this is going to start 2 independent tasks within this task here, right? And each of them gets submitted to the pool. Each of them goes to run guarded, and one does a withdraw and one does a deposit. And then it's going to return completable future all of, and it's going to give you the withdrawal and the deposit. So what this is going to do is for n tasks, it's going to create n tasks. Each of those n tasks is going to spawn 2 tasks, one to deposit $1, one to withdraw $1. And then it's going to wait for all of those things to finish. Okay, and it's going to work inside the run guarded. And then at the end of all that, when all of those things are finished, it's going to do this then run, which is just going to be a void task, right? Just a runnable. And it's going to do a run guarded on bank, and it's going to get the balance and assert that the balance is equal to the number of failures, right? So that means we tried to withdraw and deposit a bunch of times. The only thing that can fail is the withdrawal. So the number of withdrawals is equal to the number of failures. If that all works, right, then our test passes. And I've got that one already queued up in my thing to run. And it got 3 failures, but no assertions thrown. So it succeeded, right? Does that make sense? All right, so let's talk about guard var and this thing that comes back, because Java hides a little bit of stuff from you. So when I do a guard var, when I do a run guarded on this thing, and I get this bank function, right? It's of type var bank. And what is var, right? Hold on. Var is over here. Okay, so var is just sort of a wrapper around this thing that implements this get and set interface, right? And this get just has a get method on it, and the set has a set method on it, right? And it's just that. So you can get and set from this var object with whatever it's guarding. So if it's an integer, right, you can take out the current integer with get, and you can put a new integer value in there with set. Does this all make sense? Are you with me? All right. R. Let's look at test bank 2. So test bank 2 introduces the condition variable. Now we remember condition variables, right, from locks, and we have something analogous to condition variables for guards. And the way it works is I have on the guard, I have run condition, and then I have bank. Okay, so I have a guard var for bank, right? And then on guard, I can create new condition for that guard, and very much like I would create a new condition with the mutex. And here, I'm going to call power for each. And when I do the withdrawal, I'm going to say, instead of just doing what I did before and counting the number of failures, what I'm going to do is I'm going to do the bank.get. So that gets the bank class out of the var class. I'm going to attempt to withdraw $1 from it. And if I succeed, then I'm incrementing withdraw count, and I'm going to mark this withdraw future as completed, right? This one. And I'm going to return true. If this fails, however, I'm going to return false. So this is kind of like the condition variable, right? If the condition isn't met, I return false, and the task and this block of code here will run again. And when will it run again? It will run again when the condition is signaled, right? So what's going to happen with the deposit is that's going to run as a run guarded. I'm going to increment my deposit count. I'm going to do my bank.get to get the bank out of the var, and then I'm going to call the deposit with $1. I will now signal not empty, right? And when I call that signal not empty, that potentially enables this condition to run again. So it works very similarly to the condition variables in mutexes, but again, it's slightly different. Instead of having again, it's a block of code. This time, instead of returning void, it's going to return a Boolean. And if it returns a true, that means it did what it intended to do and it's done. If it returns a false, it needs to be run again on the same guard. Okay, and that's the way condition variables are implemented with guards. Now, because we can't solve the halting problem, because nobody can look at a block of code and decides whether it terminates or not. That's an unsolved problem in computer science, right? That means it's possible for you to create, deadlocks and locks and things if you misuse condition variables, because you can put any kind of logic in there and you can mess anything up if you just you could just make a loop that never ends. You could put something in your condition that says always return false, and then it's never going to complete, right? So you don't have all the same guarantees with conditions because, as I said, you can't solve the halting problem. But you've got the basic problem with guards is still solved. Does that all make sense? All right, good. Now let's take a look at test bank 3. So in test bank 3, we're going to do something similar, but this time we're going to have two bank accounts, right? We have A and B. And what we're going to do inside our par for each this time, we're going to go from 0 to n. And what we're going to do is we're going to have three things in here. We're going to have a withdrawal, we'll have a transfer, and we'll have a deposit, right? So one of these bank accounts, so the A bank account is going to have withdrawals processed on it. The transfer is going to happen with A and B, right? And hold on, where is? Yeah, so B, this thing called B not empty is a new condition that's made from A and B, right? So what's going to happen is with this condition, when this runs, it's going to have both bank A and bank B. And what we're going to try to do is withdraw from one and deposit to the other. And if we do, we're going to succeed and return a true. Otherwise, we're going to return a false. So that's a transfer is going to have to essentially lock, if you want to think about it this way, both bank accounts. Withdrawal and deposit only need to let's not say lock, let's say serialize on one of them. Okay. And so now I've got, instead of having two guard tasks running for each of these items in my par for each, I'm going to have three. Instead of deposit and withdraw, I'm going to have deposit, transfer, and withdraw. So this stresses out having multiple guards for a single task. And at the end, I'm going to do a then run, and I'm going to get the balance. And I'm going to make sure that the number of withdrawals that equals the withdrawal count equals the transfer count, and the transfer count equals the deposit count, and the withdrawal count is equal to n, which is the number of things that we did, right? So those are the assertion statements there. And done.join is getting the balance from bank A, and it's got to be 0, right? Because all the deposits into A have to work, all the transfers from A have to work, right? So let's run that one. Well, let's run 2. I'm sorry, that's still 1. There's 2. And it also succeeded, right? And there's 3. And it prints out the withdrawal count, the transfer count, and the deposit count. So, is your mind blown? Questions?
So this one is an example of composability, right?
Yeah.
And then, so you can have no cycles within the same guard, assuming there's no conditional variables or something. But you can have different guards in the same program. Well, yeah, but they can't deadlock because of.
Right.
Okay. I guess if you have like a subtree of a tree, it's still gonna be.
There's a Fibonacci here, but that's not relevant because it's just futures. There's no guards. I have a read-write guard, test read-write guard. So this was my read-write guard class that I developed using guards. And it turned out to be reasonably tricky to write. So it's going to keep track. The way it's going to work, it's going to have a single guard. It's got a single condition for that guard, and it's got a parameter called balance, which more about that in a minute. While it's running, it's got a read count. That's the number of threads that are currently reading. It's got a write waiting and a read waiting count, and it's got this method called writer's turn, which is going to be true if it's the turn of the writer. And the way that's going to work is we say write waiting times balance is greater than read waiting. So that's just a way to sort of balance the number of reading and writing tasks that get through. And then I have run read, which has a runnable, and it has an anchor waiting. And this method isn't meant to be called directly by the user. That one is so there's run read guarded and run write guarded. Those are the methods that the user's intended to call. And what we're going to do is we're going to say run condition new con check 0. So that's the type of the method that goes there, which you haven't been exposed to because of the Java Lambda syntax. And this time I'm not using the Lambda syntax because I want to give this anonymous inner class a Boolean field named anchor waiting. And then the method that gets run is named check. And what I'm going to do is I'm going to get this anchor waiting from the class, and I'm going to then mark it as false and pass it to run write. So the idea is when this runs, the first time the condition task attempts to run, it has a true, and all the other times it has a false. Does that make sense? And I'm going to do the same thing with the read tasks, right? I'm going to have a field variable anchor waiting, and the first time it runs, it's going to get a true, but all the other times this check method runs, it's going to get a false. Okay, and so if I go and I look at run read, I've got the task to run, and I've got the anchor waiting. And if anchor waiting is true, I'm going to increment read waiting. If it's the writer's turn, then I'm going to return false. If it's not the writer's turn, I'm going to decrement read waiting, increment the read count because I'm now running, and I am going to run the read task, right? And then when it's done, I'm going to make sure that the read count is decremented, and that everything that was waiting, it gets signaled. You following all that?
So it waits until all the ones that were waiting to be read are read.
Yes.
Signals to them.
Yes.
That makes sense because you can't write it someplace.
And I have this future here, which I don't use, which is interesting. That's silly of me. Okay, and then I have a run write, and that's actually slightly simpler. So it's going to anchor the waiting. It's going to check to see that the read count, if the read count is greater than 0, or if it's not the writer's turn, it's going to return false. If it is the writer's turn, it's going to run. It's going to decrement write waiting, signal all, and return true, right? And so what this gives you at the end of the day is a read write lock, so that test read write guard. Okay, so in this one, I have a read write guard G, and then I have I schedule tasks to run write guarded or run read guarded, right? And they're going to print something out, and they've got a unit of artificial work that they do, right? Which in this case is just sleep. And I somehow went to test fib and fooled myself. Okay. And it's got a unit of artificial work that it can do. And then it's just what it's gonna do is another one of these par for each things, right? And just launch a bunch of tasks. I think there's like 10% of them are write tasks and the rest are read tasks. And then we just ensure that we get the right number of writers and readers run at the end. And that should be, it's not in here, so I have to schedule that one. I have to call this one this way. And this should fail because, yes, because this will fail. This failed because I didn't have assertions on. Let me edit, modify options, add VM options, minus EA. So these tests are all designed to only work if assertions are enabled, because if assertions aren't running, then we're gonna not. It's not going to be it's not, the test's not going to work because we're using assert to make sure things are correct. And the way we do it is we have this test that require assert. And the way this works is we attempt to assert false. If this code triggers an assertion failure, then we go to the catch block and nothing happens. But if assertions are not enabled, then we execute this throw new error that says, please enable assertions. So that's just a, safety check. Okay. And so when this ran, right, we see reads and writes coming with a ratio of about 1 to 5, because that's what I said the balance was. So we have a read-write lock. That was your question, right, Tristan?
Yes. Would be very helpful.
Yep. So that's pretty much everything. There are some more examples I can show you. Here's one. We don't have enough time to go all the way through it, but I'll get started on it at least. So this is something called the heat equation. Does anybody here know what the heat equation is?
Hopefully so.
Yeah, it's something to do with heat, right? It's a way to numerically solve a so-called parabolic differential equation. And I should have had a better slide for this all ready to go, but I'm just going to trust the internet and say heat equation and go to Wikipedia and hope that this is going to show me everything the way I want it to look. So the heat equation is going to look like this. We're going to have the partial derivative of u with respect to t is equal to a second derivative of u with respect to x. And you could do it in multiple dimensions. If you do it in one dimension, you can think about this as the heat equation to describe the heating of a piece of spaghetti. Okay. And the way we want to solve this numerically is, let's see if they do that in here. Kind of, it looks like. Well, okay, so if you take solutions, right, what you can do is you can like hold the endpoints fixed and then allow the heat to just propagate until you get something that's like a straight line between the two endpoints. But you can watch the heat slowly diffuse through your noodle, say, if you want to think about it that way. What we're going to do, if you look at this equation, is you know how you remember in your calculus class, du dt, right, is this infinitesimal, you take this limit, right, as delta t gets very small and the function takes on this specific form. Well, what we're going to do when we want to solve things numerically on a computer is we, instead of taking that limit of delta t goes to 0, we just set it to something small, where small can mean 0.01. right? And instead of doing a true derivative, we do what's called a finite difference. We say u of t at our next time equals u of t at our current time plus delta t times, hold on. Where's our first? Plus delta t times alpha du dx squared, right? And I'm going to ignore the y and z terms because I've just got a noodle. I don't have a three-dimensional space, right? So I'm going to say this is delta u and this is delta t. And I'm just going to put, and so delta u means u future minus u now. And that means I can solve. I just need something to type on that you can see. So I have du dt, right? Equals u future minus u now over del dt, where dt is some small number, right? And the heat equation says du dt equals alpha times du dx or ddx squared of u, right? So what I can do right, is I can say u future, if I could just do some algebra here, and I can say u future equal u now plus dt times alpha times d dx of u, right? And what I can do with this is I can have a grid with a bunch of different points, and I have the heat stored at each point. And I'm going to calculate this value at each point, and I'm going to use it to update u at each point with a new amount. And the way it works is it's kind of like averaging, right? When I'm also going to, just as I changed this du dt into a finite difference, I'm going to do that with the du dx squared. And at the end of the day, I'm going to have something like u future equal, well, how best to do it. So I'm going to say I'm going to have the time and then the spatial position, right? And I want to know u at the next time. It's going to be u at the current time and position plus dt times alpha over 2 times dx squared times u of t x plus 1 plus u of t x minus 1 minus 2 times u t comma x. So I'm not showing you right now how that all comes about, but this essentially is the thing that you wind up having. And this says you can evaluate this at each step, and you can add it to what's currently there to get what's going to be there in the next time step, right? So it gives you a procedure that you can follow to simulate the heat equation. And I'll try to do better with that explanation next class to give you more of a feel for where this comes from. But the idea is we have a grid of values. We have a way to update those values that represents taking them from one time to another time. And we're just going to do that sequentially a bunch of times. And we're going to evolve the temperature of it. And using that, we're going to evolve the temperature of a noodle. Now, when I do it, I'm going to have a periodic boundary conditions, which says that the noodle is going to be in a loop. So I'm going to start with some heat profile where one end of the noodle is hotter than the other, and the heat is going to diffuse through the noodle. And we're going to do that in parallel on a computer. Any last questions? Yeah, I need to do better with that explanation. I need to have a prettier slide for heat equation. Oh, that's what I should show you. No, yeah, no, well, hold on. Let me end the class first.